Hello again. I'm interested now to discuss and continue to the concept of quantization. Quantization. What is that? Always we use this word and we listen in the movies, in cartoons, in the market, in the subway, wherever you go, always you can read and listen the word quantum. What is a quantum? Okay? What is a quantum? Why we have quantization? What is this effect? Where comes from? Okay, I won't explain deeply the concept of quantization. Just I will introduce what we understood about quantization, or what are the tools that we use to quantize something. We already talked about the scales problem, and the nature at the scale of -9, 10 to -9 meters approximately, like in scale of nanometers, actually I can, there are some, okay, from 100 nanometers to 30 nanometers, and from 30 nanometers to 1 nanometer. Okay, in this scale from 30 to 1 nanometer, the quantum effects are more visible, or is experimentally it was seen that in the from experiments, usually from 15 nanometers, of course this value change and vary depend on the system that we are studying, but the quantum effects are near to this from 10 nanometers to more. Okay, let's start from, okay, to, okay, something like this, near to 0. Okay, I mean, when you are, okay, this is, I don't know, but near to the 0, when we have from 10 nanometers, 100 nanometers, appears quantum effects, but more from this scale, from 30 nanometers to 1 nanometer. This is the region which now I am discussing. I am not take into account now more smaller scales. For example, in string theory, or we can work on also in 1 times minus 15 meters, that is one fair. That is the scale with we work in nuclear physics. Okay, but what is a quantization? I told that the nature among these scales, between those scales from 30 nanometers and 1 nanometer, appears new interesting effects. That is just that the nature has a behavior of waves. If you have a tree, for example, we have here one tree. This is in classical mechanics. But now when we have the quantization, or when we reduce this tree, let's consider that a quantum tree. This is in 1 meter. Let's consider this 1 nanometer or 10 nanometers, for example. The behavior of this tree is kind of different. It's not proper a tree. It's a distribution of probability to get a tree, and is quantized. I mean, there are some available levels of energy. In macroscopic scale, the energy, this is continuous. The energy. Energy is continuous. And when we goes to the quantum size, the energy is not continuous. What does that mean, that is not continuous? It's discrete. I mean, here we have a continuous energy, and here we have we have a discrete spectra of energy. This energy is E1, E2, E3. Here the spectra of energy is discrete. What it does mean? That here the tree cannot, at first, in macroscopic scale, the tree can move wherever you want, because we don't have high effects of quantum mechanics. When we have a quantum tree, the tree cannot be wherever you want to go. Only there are allowed states where they can be. There is something else that is important to take into account, that is, in quantization, when we are in quantum area, we have something like states. State. And state, when we have, for example, our tree will be our quantum state of a tree. And there are some available levels of energy. This energy, this is the ground state. the first excited state of this tree, second excited state, and third, and so on. This is the quantum tree. Okay? This is our quantum tree. Quantum tree. So, there are only few available levels of energy which the tree can occupy. And the quantization appears that the energy is not the energy which when this for example when this tree is in this level, for example this level, and therefore the tree ups to this level and therefore return back to the ground state, occurs something interesting, that is that the tree will emit energy, and this energy is the energy of a photon and the energy of emission is h bar frequency. This is the energy of the emission of this photon, and this number that is h bar comes from h bar is equal h over 2p, and this h is the constant, Planck constant. The quantization appears when you have a discrete spectra of energy. When you don't have continuous spectra, when you have a continuous spectra, you have a classical mechanics. In quantum mechanics, you have discrete levels of energy. Also, there is, the formalism doesn't have trajectories of the particles that are in quantum mechanics. There are only densities of probabilities of the tree, but it doesn't mean that the tree cannot move. The tree can move, but we don't know the trajectory. We know only the density of probability which the tree can be. It's a density function that is the probability. Let me write, here, the probability. The probability, and I will finish. Probability. Ability is the wave function square. Okay, is the square wave function. Okay, initial final function. Well, later I will explain more about this probability, but now the important part is that the quantization okay, the quantization comes from the quantization comes from the discretization of the energy, and also the quantization is an effect that appears when we assume a boundary. The discretization in the wave function appears when you put the wave function inside a potential, where inside is potential in order to solve the differential